So we are discussing the quantum mechanics of particles moving in a central potential. Yes. So central potential, I remind you, is one in which the potential is only a function of the absolute distance and does not depend on the angular coordinates, theta and phi in spherical polar coordinates. Okay. So we discussed that the way to set this problem up would be to look for the simultaneous eigenfunctions of the Hamiltonian and L square and Hamiltonian and the L3 operator. Okay, so notice that L square and L3 do commute. Okay, but L3 does not commute with L1 and L2, so we look for the simultaneous eigenfunctions of H, L square and L3 operator. We might as well look for simultaneous eigenfunctions of H, L square and L1 or L2, but L3 is the conventional choice. Okay. All right. So given this, we explicitly proved that these commutation relations are indeed true in the lecture before last. And yesterday, we worked through the mathematics of these operators to establish the Schrodinger equation for particles traveling in such a potential, which is the boxed equation that you see on the screen. Okay. Along the way, we also wrote down a nice formula for del square in terms of the angular momentum square operator L square, which is this formula. We will come back to this formula in this lecture also. But for now, let us begin with the boxed equation, which I will rewrite again. Okay. So the Schrodinger equation for this particle, whose mass I'm calling mu, is given by ddr r square d psi dr plus L square over 2 mu r square acting on psi of r vector plus v of r psi of r vector equals e psi of r vector. Okay, so notice that psi is in general a function of all three coordinates r, theta and phi, but the potential is only a function of the distance r and not theta and phi, so which is why I've written v as a v of r and not v of r vector. Okay, all right. So we are looking for the simultaneous eigenfunctions of H, L square and L3. The way at this point most textbooks approach this problem is to write down the differential equation for L square and proceed to solve it. And that indeed is the correct approach. But let us actually try and push forward to delay solving this differential equation as much as possible and try to guess things about the solution as much as possible. At some point, we will have to solve the differential equation, but for now, let us sort of discuss the physics of this equation as much as possible. Okay. Now, let us look at this differential equation and let us look at the limiting case when how does psi look like at points very, very close to the origin. Okay. So let us look at points very close to the origin are equal to 0. Now, sorry, Niyati, I'm hoping that you will admit all the students who joined.
Yes, sir.
So Harshavardhan is asking, why is the wave function independent of theta and phi? No, I am not claiming the wave function is independent of theta and phi. The wave function does depend on theta and phi. That's why I've written psi as a function of r vector. Okay, r vector knows both about r and the angles. In other words, psi is a function of r, theta and phi. It is only the potential that doesn't know anything about the angles theta and phi. Okay, is that clear? All right. So you should be careful when looking at this equation. When I write r vector and when I just write the distance r, those are two different things. R vector depends also on orientations. All right. So suppose if I am looking at distances very, very close to the origin. Okay. Now, if the potential itself, now we have not discussed what the form of the potential is, but if the potential itself is not singular at the origin, highly singular at the origin, singular meaning things blow up, I would expect the wave function to be a smooth function of the coordinates, right? So let me please share, because this has started causing problems very early today. All right. Okay. So as r goes to 0, I would expect that psi is a smooth function of the coordinates x1, x2, x3. Okay. Or xyz equivalently, but I'm using x1, x2, x3 in this lecture. Okay. Now, this is a reasonable assumption to make. Now, if psi is a smooth function of x1, x2, x3, it goes to, it's really should be okay that psi can be written as some kind of a power series in x1, x2, and x3. Okay, because any smooth function can be expressed as a power series close enough to some point which we call as r equal to 0 in this particular case. So I can write psi as some kind of a polynomial function in x1, x2, and x3, which are the coordinates. Okay, so notice that I'm going to argue what the form of the wave function should be like. So at any point in this argument, if you have any questions, please stop me. Okay, so now since I'm looking at distances that are very, very small, very close to the origin r equal to 0, if I expand psi as a power series in x1, x2, and x3, I'm really looking at the lowest power that is there in this power series. In other words, if, for example, if psi very close to the origin, it turns out that can be written as something like a x1 cubed plus b x2 square plus blah, blah, blah. At very close to the origin, roughly speaking, the x2 square part will be more important than the higher powers, because we are looking at distances very close to the origin. Okay, so I'm looking at the lowest power of x1, x2, or x3, or some function of x1, x2, and x3. So what is this lowest power that I'm looking at? So let me call that the wave function, some wave function depends on the lowest power of x, the lowest power. So in other words, let me write this down. One expects psi to be a homogeneous polynomial in x1, x2, x3 close to the origin. Okay, to be very explicit, homogeneous polynomial in x1, x2, x3, what does this mean? A homogeneous polynomial can be of any order. So if the homogeneous polynomial is of order 0, then it depends on x1, x2, x3 to the power 0, which means this is basically a constant. Okay, a homogeneous polynomial of order 1 would be some linear combination of these guys. Okay, a homogeneous polynomial of order 2 can have various terms like x1 square, x2 square, x3 square, but not just that, I can also write down terms like x1, x3, x1, x2, and x2, x3, right? And the homogeneous polynomial of order 3 would be x1 cubed, x2 cubed, and all cubic terms, and so on and so forth. So I expect psi to be a homogeneous polynomial in x1, x2, x3 close to the origin. I don't know what the power of the polynomial is. It can be of order 0, order 1, order 2, whatever it is. That I would know only after I solve the equation. But this is what I can roughly expect. Okay, very close to the origin, I can write things as a power series, and I simply look at the lowest power, whatever the lowest power is. So let's call the lowest power of psi to be L. Okay, in other words, very close to the origin, psi can be written as a homogeneous polynomial in x1, x2, x3 of power L. Here L is some number, 0, 1, 2, 3, whatever it is. I don't know what the order is, but I'm simply assuming that it is some power of x1, x2, x3. The power is L. Okay. So in terms of spherical polar coordinates, which means that my psi can be written. So let's take the example. Let's take an example of order 2. So if I have L equal to 2, for example, what do I mean? I mean that my psi has powers of x1, x2, x3 like this: x2 square, ax1 square plus bx2 square plus cx3 square plus dx1 x3 plus ex1 x2 plus fx2 x3. Okay, I'm guessing that my psi looks something like this. Now I can write this entire thing in terms of, excuse me, r, theta, and phi in spherical polar coordinates. How does it look in spherical polar coordinates? Remember that x1 is r sine theta cosine phi, x2 is r sine theta sine phi, and x3 has no dependence on phi, it is just r cosine theta. So this homogeneous polynomial of order 2 in spherical polar coordinates can be written. Remember that everything is second power in excess, so there is an r square that can be just factored out. So I can write this psi as r square times some function of all the angles, right? The first term is a sine squared theta cosine squared phi plus b sine squared theta sine squared phi plus blah, blah, blah. Okay, this is simply a function of theta and phi because all the r dependence factors out. Similarly, if psi is a homogeneous polynomial of order 1, I can write this as r times a sine theta cosine phi plus b sine theta sine phi plus c cosine theta. So in other words, if psi is a homogeneous polynomial of order L, excuse me, I can write psi as r to the L times some horrible function of theta and phi, which I will simply call y of theta and phi. Okay. So in spherical polar coordinates, a homogeneous polynomial of order L can be written as r to the L times some function of the angles which you do not know. And I also don't know what L is. I'm simply assuming that close to the origin, the wave function has this particular functional form in r, theta, and phi. Okay, so this is my starting point. This is my assumption. Now notice that this y is only a function of angles. It doesn't know anything about r at all. Okay, because all the r is factored out, like I have demonstrated for a simple case in the line before. Okay, so with this information, let us revisit our Schrodinger equation and look at this Schrodinger equation for distances very, very close to the origin. Now, before I do that, let me rearrange this Schrodinger equation, which I've written here, as an equation for L square. So I can rearrange this equation trivially to write L square psi of r equals h bar square ddr r square d psi dr plus 2 mu r square e minus v of r times psi. This equation is exactly the same as the equation above. Is psi being homogeneous near origin assumption? Yes, it is an assumption, and it is a very reasonable assumption to make. It is a reasonable assumption to make because ultimately we want normalizable wave functions, right? So we want normalizable wave functions, which means we should always have wave functions that do not blow up at infinity, and they should not also be badly behaved near the origin. These are two places usually where wave functions can blow up. Okay, so as long as I have a wave function that is reasonably well behaved near the origin and reasonably close to the origin, such a wave function can always be expressed as some kind of a power series in the coordinates x1, x2, and x3, assuming that it is a smooth function of x1, x2, x3. That is, there is no discontinuities near r equal to 0. If this is true, this is a reasonable assumption to me. All right. So this equation that I have written down is exactly the same as the Schrodinger equation I've written above. I've simply rearranged the terms and I've pushed this ddr to the other side and multiplied through by 2 mu r squared. Okay. So this is basically the Schrodinger's equation for the central potential V of r. So with our logic, above, that psi has to follow that particular form for distances very close to the origin. Let us investigate this equation and ask what this equation looks like. So if r goes very close to 0, then the first term should be evaluated assuming the ansatz psi equal to r to the L y of theta comma phi. Now, how about the second term? The second term has an r square multiplying e minus b of r. Okay. Now, up till this point, we have not made any assumption about v of r. V of r can be 1 over r square, or r, or anything that is function of distance alone, right? Now, if v of r is simply a function of r, like, r square, r cubed, or whatever it is, when r goes to 0, the second term will go to 0, right? Because there is no compensating term in v of r to cancel the r square that is multiplying this whole thing. So this r square will tend to make this term go to 0 near the origin r equal to 0, unless, for example, v of r is proportional to something like 1 over r cubed. If v of r goes like 1 over r cubed, then r square times 1 over r cubed is 1 over r, and that becomes singular at the origin. So if I'm restricting my attention to those potentials that do not become more singular than 1 over r square, assume that v of r is not more singular than 1 over r square as r goes to 0. What does this mean? It means that v of r does not have something like 1 over r cubed or 1 over r to the 4 or things like that, because those guys will diverge at the origin, and the r square will not be enough to compensate for it. As long as v of r is 1 over r square or something less singular, then the second term, I can argue, will always go to 0 as r goes to 0. So this is an assumption that I'm making about the potential at hand. I'm not just looking at central potentials, but I'm looking at those potentials that are 1 over r square or less singular at the origin. Notice that if you simply solve the differential equation, such an approximation would not be needed. But since I'm arguing my way out of this differential equation, I'm simply making some reasonable assumptions. So for example, for the Coulomb potential, v of r is 1 over r. So this is perfectly valid assumption. All right. So if I look at this equation for r goes to 0, then the left-hand side is L psi of r equals, the second term vanishes, and the first term is h bar square ddr acting on r square ddr of r to the L y of theta phi, because that is the form of the wave function close to the origin. So evaluate this, you will get, now y is a function of angles alone, and the ddr will not have any effect on it. So I can pull the y of theta phi out times h bar square ddr of r square. ddr of r to the L is L r to the L minus 1. Okay. Now, if I push this further, I will see that this is equal to y of theta comma phi h bar square. The L is just a constant, and r square times r to the L minus 1 is r to the L plus 1, sorry. So this is ddr of r to the L plus 1. This is basically h bar square L plus 1 r to the L y theta of phi. Okay, but you recognize that r to the L y theta of phi is simply our wave function psi. So at distances very close to the origin, the Schrodinger equation for the central potential basically reduces to L squared psi of r equals h bar square L plus 1 psi of r. Okay. This, you recognize, is basically an eigenvalue equation for the operator L squared, right? So this is an eigenvalue equation for the L square operator. Okay. Now, before I move on, are there any questions about the reasoning behind any of these things up till now? Any questions? You can unmute and ask, or you can just type in the chat window. Okay, so let us recap what we have done. We have looked at this equation close to the origin, and we have said that psi close to the origin should have a form like r to the L y of theta comma phi. And once I assume that psi does have this form, I can plug this back into the Schrodinger equation for very small values of r and ask what this equation gives me. And this equation basically tells me that psi, which is an eigen, so remember that psi is an eigenfunction of h, the Hamiltonian operator, right? Because this equation is basically h, where's this equation, Schrodinger's equation is basically h psi equals e psi. So psi is basically the eigenfunction of the Hamiltonian operator. But when I investigate this equation for r very close to the origin, I find that this psi is also an eigenfunction of the L square operator. And this is precisely what I want, because I started this lecture by claiming that I want to find out simultaneous eigenfunctions of h and L square. Okay. But now you might object, saying that this psi would only be an eigenfunction of L square if r is very close to the origin. If r is not very close to the origin, then I cannot just throw away the second term in this equation, and I will have a completely different psi. And that psi, you would say, might not be an eigenfunction of the L square operator. Is this clear? So we have argued that this equation, when looked at regions very near the origin, turns out to be an eigenfunction of the eigenvalue equation for the L square operator. But now we have to look at distances not just close to the origin, away from the origin also.
Sir?
Yes.
Sir, instead of choosing psi in this way, why don't we taking the Taylor series expansion of psi at the origin?
Why don't we take the Taylor series expansion of phi?
Because sir, I'm very bad at guessing things and I don't understand this very well, because you said it's homogeneous, but the power is x square and x1 x2, there is product of two different yes, but sir, homogeneous should be linear, right? But this is not linear, this is quadratic form.
No. I am not claiming it should be linear in x1, x2, x3. That will be a very strong assumption to make, right? See, ultimately, what should I do? I should simply treat this equation, excuse me, as a differential equation and should solve this differential equation, right? And that is what I will ultimately do. But before I solve for this differential equation, in physics, it's always useful to understand certain limiting cases and what this equation tells us. Okay? So a typical standard textbook way of doing things would be to simply say that psi is a function of r alone times a function of theta and phi alone, right? And then proceed to plug this back into the differential equation and solve for it. And that is perfectly okay. But what I'm trying to do here is try to motivate why that form is true. Okay, so why is it that I can write psi as a function of r alone times some function of theta and phi? I'm simply trying to motivate it on physical grounds. That is my motive here. That is part one. Part two, the answer to your question is, you can always write psi as a Taylor series expansion. Fair enough. But what is a Taylor series expansion? Ultimately, see, I do not know what the functional form of psi is, right? It can depend any which way it wants on x1, x2, and x3. Agreed?
Yes, sir.
So whatever I do, if I write the Taylor series expansion, I will ultimately get some kind of a power series expansion.
Yes.
Which can have powers like, x1, x1 square, x2 square, x3 square, or x1, x2, whatever it is. So if I Taylor expand a function of multivariables, I should Taylor expand in every single variable.
Yes.
Right? So I can have terms like x1 square, x2 square, x3 square. I can have terms like x1 cubed, x2 cubed, x3 cubed, but I can also have terms like x3 square, x2, x2 square, x3, whatever it is, right?
Yes.
So I do not know at what order I should truncate, right? But what I do know is this. Suppose if for a given wave function, I have all these orders,
since I'm looking at distances very close to the origin, in some sense, I know that x1 to the 4 is going to be less important than x1 cubed. Because I'm looking at distances very, very close to the origin. So x1, x2, x3 are all very small quantities. Make sense?
Yes, sir, makes sense.
So in this way of looking at things, logically speaking, if I have a power series expansion or Taylor series expansion or something, all I have is a collection of polynomials. And I am looking in this expansion, I'm simply looking at the lowest order polynomial in this expansion, because the lowest order polynomial is the one that is going to contribute significantly very near the origin. Does this make sense?
Yeah, sir.
And I do not know what the lowest order is, so I'm simply calling this lowest order some L. It can be 1, 0, 2, 5, whatever it is. For that, I have to solve the differential equation.
Yes, sir.
So with this assumption, I can argue that my psi very close to the origin is going to look like r to the L times y of some function of theta and phi. Now, when I plug this back in the Schrodinger equation, I get an equation which is an eigenvalue equation for L square. Okay, sorry, this is again stopped responding. Now, let us look at this further and simply try to argue our way out of this. What would happen? So would this eigenvalue equation still hold if I'm looking at distances far away from the origin? Okay. What if this assumption is not true? What if you are not looking at r close to the origin? Well, if you stare at this equation, which I've put as a tick mark here, notice that L square is a function of angles alone. It does not depend on the distance r. So if you look at the formula for L square, I don't know if I've written it somewhere. Okay. Oh, yes, I have. Okay. So if you look at this formula for L squared operator, it is a function of only theta and phi. Okay. Which makes perfect sense because L does not change the distance from the origin. It only rotates the particle, right? In the theta and phi directions. So L square only talks to the angles. So if I write this equation, what this equation really means is that the r to the L part of this wave function cancels on both sides. And this is basically saying L square acting on y theta of phi is h bar square L plus 1 y theta of phi. Okay. Now, if I go away from the origin as r keeps increasing, of course, I don't expect my psi of r to still be of this form, r to the L y theta of phi. Okay. But if I'm keeping theta and phi constant, I'm simply changing r, my psi would change because the r to the L part will not be true anymore. But I'm not changing y theta of phi. So which means I'm really not changing the eigenvalue equation for L square. So I can argue that as I go away from the origin, my wave functions should still be an eigenfunction of L square, because at very close to the origin, it was an eigenfunction of L square. But as I keep increasing r, all I'm doing is increasing the radial coordinate and not doing anything to the angles. So at distances far away from the origin also, my psi should still be an eigenfunction of the L square operator. And I can ensure that the psi far away from the origin is also an eigenfunction of the L square operator if my psi has the general form r of r times y of theta comma phi. Okay, with the assumption that, or with the constraint that this function r of r, whatever it is, should look like r to the L as r goes to 0. In other words, all I'm saying is as I increase r, this wave function should change only in the part that is multiplying the y, and the y itself cannot change. Okay? Which means that even as I go away from the origin and my radial part of the solution changes remarkably, the wave function still remains an eigenfunction of the L square operator, because L square only acts on the angles. It doesn't know anything about the r. So L square acting on this r psi is simply L square acting on r of r y theta of phi, but it doesn't do anything to the r of r. So this is L square, sorry, this is r of r times L square acting on y theta of phi. Okay, but L square acting on y theta of phi, I already know it's just h bar square LL plus 1 y theta of phi. So this is and this is simply h bar square LL plus 1 psi of r. Okay. So by simply looking at the form of the wave function very close to the origin, I can deduce that the form of the wave function at all distances r should have this particular form. I could have started by simply claiming this, as many textbooks do, but it is useful to understand where this comes from. At all points in this derivation, all we are looking for at every single stage is to look for simultaneous eigenfunctions of h and L square and also L3. Is this logic clear to everybody? Are there any questions or any comments about this particular step? And are you guys convinced that psi of r for this particular problem should have this particular form in the green box?
Hello, sir.
Yes.
Sir, when we are solving Schrodinger equation by parts or the separation method, sir, all this problem, does them have this similar kind of argument?
So ultimately, see, this is basically separable method, right? Separable method is saying that if you have a differential equation in x, y, and z, you simply assume that it is a function of it's something that is a product of the functions of the different variables, right? Psi of x, y, z is f of x times g of y times h of z. Now notice that that is a very strong assumption. It's a strong assumption because there is no reason, before you solve the Schrodinger's equation, there is no reason to assume that your function should be only of this form. For example, sine of x, xy, right? It is not of the form f of x times g of y, right? Because sine of xy, it cannot be written as some f of x times g of y. The logic here is that the Schrodinger equation is a linear equation. I can always take linear combinations of the solutions, and that will also be a solution of the Schrodinger equation, right? So at the end of it all, your most general solution would be a combination of all these particular solutions. And that will not have the form of f of x times g of y times h of z. Okay, so that is a logic that you adopt when you use the variable separable method in solving Schrodinger's equation. What I'm doing here is mathematically ultimately exactly the same, but I'm hoping that it will be physically more obvious to you why I'm choosing it in this particular form. Because if you simply look at this equation and argue what happens to Schrodinger's equation, oh gosh, what happens to the Schrodinger's equation in this case for distances close to the origin, the eigenvalue equation for L square pops out. Okay, and then you can basically argue that if this is a solution at distances close to the origin, then this has to be the solution for distances away from the origin. But I could have, as you point out, I could have just started by saying this, right? I would say that I'm going to solve this equation by assuming that psi of r is r of r times y of theta comma phi. It is certainly okay, but to me at least it doesn't. I don't know, this method that we are approaching to me makes more physical sense, but you pick your poison. If you simply like the ansatz here and you can just start with this ansatz, that is perfectly fine also. But ultimately you should convince yourself that this is not the only solution. There can be linear combinations of these solutions. That would be the most general solution. Okay. Any other questions or comments?
No, sir.
Okay. All right. So notice that now we have explicitly constructed a wave function that is an eigenfunction of both L square and h. Now it is very easy to show that this will also be a function of eigenfunction of L3 operator because L3 and L square commute. Okay. So again, L3 is also a function of only the angles. In fact, L3 is a function of only phi, not even theta. So I will assume that the eigenfunction of L3, y is also an eigenfunction of L3 with an eigenvalue given by mh bar. Okay. Now, why mh bar? Well, H bar has the units of angular momentum. L3 is an angular momentum. So L3 should measure everything in terms of units of angular momentum. So the H bar is a very natural choice here. Now, I don't know what unit of angular momentum, so I'm using some m, and m can be anything at this point. I don't know what m is. But I can quickly restrict m in one step by looking at what the form of L3 is. Remember that L3 is minus IH bar dd phi. So if this equation can be rewritten as minus IH bar dd phi of y of theta comma phi equals mh bar y of theta comma phi, and the h bar cancels, and I can rewrite this equation as d of y of theta comma phi over y of theta comma phi equals, what is this? Im d phi. Okay, and I can integrate this equation to obtain y of theta comma phi is e to the Im phi times some function of theta. See, this only pins down the functional form of phi. It doesn't say anything about theta, so y can still be some function of theta and solve and still satisfy this differential equation. So this is the general solution of y. Okay, so y of theta comma phi, this angular dependence is e to the Im phi times f of theta. Now we can restrict the possible values of m by claiming that y should be single value. So in other words, y of theta comma phi, and since phi can go from 0 to 2 pi, and 2 pi is 360-degree rotation, it should bring you back to the exact same point. So this has to be y of theta comma phi plus 2 pi. Okay, because wave functions have to be single valued. If they are not single valued, they have a huge problem, because psi square is a probability, and if you have multiple values at every spatial position, then your probability interpretation will be lost. Okay. So what does this mean? This means that e to the Im phi f of theta should be equal to e to the Im phi plus 2 pi times f of theta, which tells me that e to the Im times 2 pi should be equal to 1. And this is trivially satisfied if m is an integer. Okay, so m can be 0, 1, 2, whatever it is, but we will restrict the number of values m can take even further, but for now we know that m is an integer. Okay, so remember that we have still not solved the differential equation, so we have gotten quite a few things for free basically. Okay, so now where are we? The solution for the Schrodinger equation for the central potential should thus have the general form e to the Im phi times some function of theta. What this function is, we will guess later, times some function of the radial coordinate r. Okay, this is where we are.
Yeah.
Yes.
How did you guess this? The factor that would the constant factor would be a function of theta.
Oh, this is a very general thing, right? So let us say that you have a function of two variables, f of x comma y. Okay, right? Now let us say that there is a differential equation for the y part. Let us say the differential equation for the y part is df dy equals, just like this guy, some k times f of x comma y. Right? First of all, this is a differential equation only for the y part. So I should actually properly write here partial, right? Now, how do you solve this differential equation? Well, you can solve the differential equation very simply by integrating, right? So df of x comma y dy by f of x comma y equals k integral dy, which is just ky. Right hand side is very easy. The left hand side is logarithm of f of x comma y equals ky, right? Now, the solution for this is f of x comma y is some constant usually times ky. But here, what is a constant? A constant in this according to this differential equation is anything that doesn't depend on y, right? So if I can multiply this by a function of x alone, and this would still satisfy this differential equation because the g of x would simply cancel on both sides of this equation. So if it is a function of one variable, then if you have an equation like df dx equals kx, you write this solution as a e to the kx, right? Where a is a constant. By a constant here, I mean that it doesn't depend on x. But here I am only differentiating with respect to the variable y, which means anything that depends only on x is a constant as far as y is concerned. So this differential equation only pins down how f depends on y. It doesn't tell you anything about how f depends on x. So f can depend on an arbitrary function of x times the e to the ky, and if you plug this back here, it will still solve the differential equation. Okay. So that is exactly what I used here. Y is a function of two angular variables, theta and phi, and this is an equation for differential equation for the coordinate phi alone. So y should depend on phi in this particular form, but this equation doesn't tell you how y should depend on theta. So I'm keeping that part arbitrary, and I'm calling that arbitrary function of theta as some f of theta. So I need another equation that tells me how y depends on theta, and then I'd be able to pin down f of theta. Make sense? Yes or no?
Yes.
All right. Okay, so what is it that we have gotten up till now? So I'm going to plug in this general ansatz into the Schrodinger's equation that I wrote down before. What was the Schrodinger's equation that I wrote down before? So minus h bar square over 2 mu r square ddr of r square d psi dr plus 1 over 2 mu r square L square psi of r plus v of r psi of r vector equals e psi of r vector. Okay. Now remember that L square of psi of r vector is now h bar square times L plus 1 psi of r vector, because psi is a eigenfunction of L square. And in the first part, in the first term ddr of d psi dr, if I plug in psi is e to the im phi f of theta, then the ddr part only acts on the capital R and does not do anything to the im phi or the f of theta. And you would actually find that the e to the im phi f of theta simply drops out of this equation completely if I substitute this entire ansatz into this Schrodinger's equation, which means this differential equation for psi of r, theta and phi now boils down to a differential equation for r alone, and this equation for r alone can be written as minus h bar square over 2 mu r square. Now ddr, not partial derivative but whole derivative, ordinary derivative, because capital R depends only on little r and not on theta and phi. ddr of r square d capital R dr plus h bar square ll plus 1 divided by 2 mu r square r of r plus v of r of r equals e r of r. Okay. So r of r is something that I have to figure out once I solve this differential equation, and I demand that the solution should be such that r of r is normalizable. In other words, remember that in 3 dimensions d cubed r is r square dr times the solid angle d omega. Okay, where r square, r goes from 0 to infinity. So if I want this r of r to be a normalizable function, I want integral 0 to infinity mod r of r square times r square dr to be less than infinity. Okay, in other words, I'm looking for normalizable solutions. Okay, so this is my condition. Now, at this point, you can employ a slight trick to make this equation look very much like a Schrodinger's equation for a one-dimensional potential. The trick is to define a new variable u, to define a new function u, which is r times capital R. Okay, and if you rewrite the equation above in terms of u by simply substituting capital R equals u of r divided by small r, you get a very nice equation that looks like this. Okay, now you should verify this. Okay, if you write the Schrodinger's equation not in terms of capital R but small u. So if I solve for little u, it means I've solved for capital R basically. Notice that this exactly looks like the Schrodinger's equation for a one-dimensional potential, h bar square over 2m d square psi dx square plus v of x psi equals e psi. Okay, except that the radial coordinate r changes from 0 to infinity and x goes from minus infinity to infinity. So r goes from 0 to infinity. That is one change. The other change is that the potential v of x is replaced by what is called v of r plus h bar square times ll plus 1 over 2 mu r square. And sometimes this is called the effective potential. And the second term is the sometimes called the centrifugal term. It is basically the term that is directly dependent on the angular momentum operator L square. Okay, so with these two substitutions, the equation for u of r looks exactly like a Schrodinger's equation for a particle moving in one dimension under the action of a potential v of r plus 1 over r square. Okay, and just like a capital R should also be normalized, little u should also be normalized, and this should be normalized according to 0 to infinity. U of r mod square dr should be less than infinity. Again, we are looking for normalizable solutions. Okay, and this equation is called the radial equation because it is an equation that only depends on the radial coordinate little r. Now, we will stop at this point today, and tomorrow we will take this up. We will take up the radial part later, but first we will talk about the y of theta comma phi a little bit more. Okay, and I want to motivate to you how a y of theta comma phi can possibly look like without actually solving the differential equation. Okay, and my starting point for tomorrow's lecture would also be that the solution is some polynomial of order L. Okay, with this simple assumption, you would actually be surprised to learn that you can guess the form of this y of theta comma phi, at least for some values of L. Not for all values of L, but I will motivate the some value. If you take u is r times r, then near origin, the form would change and become r to the L plus 1 and contradict our assumption at the origin. No. So, okay. Remember that the differential equation also changes. Okay, so at this point, I'm simply saying, again, I don't have to use small u at all. I can simply take capital R, okay, and simply solve the differential equation. U offers no additional insight to me that our capital R does not offer. The only advantage is that if you look at it in this particular fashion, the Schrodinger's equation boils down to something that you might be able to recognize more easily as an equation for one-dimensional motion. Okay. Certainly, if I use a different variable, the equation will change and my assumptions will change, but this doesn't change anything about my starting point. My starting point is simply the Schrodinger's equation for the variable small r and theta and phi. Okay. So this whole u thing is only because after all is said and done, this equation is sort of a little, so this equation that I'm marking seems a little unwieldy, but this equation looks a little more simple because you have seen the one-dimensional motion already. Okay, that is all. I am not claiming that the small u is any more fundamental than capital R. Okay, so I'm going to stop at this point, and please do ask if there is any questions.